Good morning, students. Today we are going for the concept of mutually coupled circuits. So now we are concentrated with respect to the ideal transformer, then followed by the numerical examples. So now what is an ideal transformer? So ideal transformer means there is no leakage flux. There is no leakage flux. So that means the degree of coupling must be equal to 1. The degree of coupling must be equal to 1. Okay. So then there is no resistance present in the coil. So which means that the copper losses must be 0. So it is negligible means must be 0. So why? Because the copper losses means I square R losses. Anyway, the current must be there. You are giving excitation, either it may be in the first coil or it may be in the second coil. But the copper losses is equal to 0 means I never be 0. So R must be 0. So under this ideal transformer, the resistance values are near to 0 or 0, either in the primary side or in the secondary side. Okay, so these are the concepts will give the ideal transformer. Under this condition, the coils having number of turns N1 and N2 with a self-inductance of L1 and L2 must be having maximum value. Must be having maximum value. Are you understanding? So now, what is a non-ideal transformer? So non-ideal transformer or a practical transformer means there must be some leakage reactance. The coefficient of coupling is nearer to 1 and there must be a copper losses due to the presence of resistance in the coil 1 and coil 2. Are you understanding? So now coming to the equations of the ideal transformer. So here I have taken a equivalent circuit with the symbolic representation of the transformer. So the two coils are mutually coupled. So V1 is the V1 is the applied voltage. So I1 is the current flowing through the first coil. V2 is the induced EMF generated in the second coil. I2 is the current flowing through the second coil. So here the first coil and second coil are entering with respect to starting dots and the mutual induction between the two coils is M. So M is a positive value. M is a positive value. So now I am writing the KVL equation for the primary side. So that is first coil side. So V1 plus J times of omega L1 into I1 plus J times of omega M into I2. So from this equation, so I1 is equal to V1 minus J omega M I2 divided by J omega L1. So now I am writing the equation at the secondary side or coil 2. So V2 is equal to J omega M1 I1 plus J omega L2 I2. So now I am substituting I1 from the above. So V2 is equal to J omega L2 I2 plus M V1 by L1 minus J omega M square I2 by L1. So for a best coupling, the value of K must be equal to Z1 and M is equal to root of L1, L2. So now I am substituting the M value. So V2 is equal to j omega L2 I1 plus root of L1 L2 V1 by L1 minus j L1 L2 I2 divided by L1. So here the numerator and denominator L1 is common. So if you go for the cancellation, so finally you can get root of L2 by L1 into V1. So that is equal to n into V1, that is equal to n into V1. So why I am taking means, so L is equal to n phi by I. L is equal to n phi by I. Are you understanding? So L1 is equal to n1 phi 1 by I1. L2 is equal to n2 phi 2 by I2. Okay. So anyway, so if it is a best coupling, the current must be same. So current is proportional to flux. So both are constants. So L is proportional to n. L is proportional to n. Okay. So by using that concept, we are writing some n into V1, that is equal to n2 by n1 into V1. So now V2 by V1 is equal to n2 by n1, that is equal to n. It is the turns ratio. So if you want to write the current, so you can get I1 by I2. You can get I1 by I2. Are you understanding? So now coming to the impedance transformation. So whenever any load is connected, so you are representing the input resistance value with respect to output resistance or a load resistance. So to understand this, so here the resistance is measured between the primary side, this side. So for this side, the resistance you are measuring, let us take that resistance value can be represented as RIN. So RIN by Ohm's law, voltage by current. So primary voltage V1 divided by primary current I1. So that is equal to, so V1 is N1 by N2, N1 by N2 into V2. So just now you are calculated what is V2. V2 is N2 by N1 into V1. So what is V1? V1 is N2 by N1 by N2 into V2. So divided by, similarly the current opposite value. So that is minus of N2 by N1 into I2, where I2 is moving with respect to rising direction. So that's why we are represented the minus side. So then finally you can get N1 by N2 square into V2 by minus I2. V2 by minus I2. So now what is V2? V2 is voltage drop across this resistor RL. And what is the RL current? RL current is I2 only. So V2 is equal to minus RL into I2. So now the value, if you substitute, so finally you can get the input resistance must be equal to N2 by N1 square into RL. So similarly, if you go for a impedance under steady state conditions of the sinusoidal excitation, so V1 is the applied voltage, I1 is the applied current, V2 is the voltage drop across the load or induced EMF generated by the two coils of the secondary coil. So ZL is the load impedance, I2 is the load current, and N1 is the turns of the first coil, N2 is the turns of the second coil. Then Z input must be equal to N1 by N2 square into ZL. ZL. So same way, whatever the resistance you are calculated, so you are replacing R by Z, that's all. Okay, so this is the impedance transformation between the coils. Next, coming to the conductively coupled equivalent circuits. So any magnetically coupled equivalent circuits you can represent in terms of conductively coupled circuits also. So inductively or magnetically coupled circuits means there is no direct connection between the elements. Conductively coupled circuits means, so it is the direct connection between the elements. So this is a inductively coupled circuit. You don't have this circuit and this circuit are directly connected, but here the two loops are directly connected. Okay, so directly connection of two loops is there, you can call it as a conductively coupled circuits. So if there is no direct connection, then it is a mechanically coupled circuits. So these circuits can be easily determined or transformed with respect to mesh equations. Okay, so I am representing the magnetically coupled circuit mesh equations. So your first loop is R1 and j omega L1. So A11 means first loop R1 plus j omega L1. So coming to the second loop, so R2 j omega L2. So R2 plus j omega L2. So diagonal elements are completed. Then half diagonal elements. So here the I2 current is leaving dot. So it is moving like this. And I1 current is starting dot. It is a starting dot. That mutual inductance must be negative. So that's why minus j omega m. Here also minus j omega m. So now unknown values are I1 and I2. And coming to the right hand side, so the first loop carries with a voltage. So V1 you are represented. Secondary side you don't have any voltage source. Blindly put 0. So this is your mesh equation. So by using this mesh equation, so I am drawing the conductively coupled circuit. So what is your A11 value? So A11 value is R1 plus j omega L1. And what is loop 1 to loop 2 value? Minus j omega m. So for that, so here I have represented the value as R1 is the resistance, j omega L1 minus m. So R and L are connected in series. So two impedances are connected in series. It is Z1 plus Z2. So finally what you can get, R1 plus j omega L1 minus m is the value. Then we are having the intermediate value is how much? Minus j omega m. So that's why here I am representing j omega m between loop 1 and loop 2. Then coming to the second loop passive elements. So the A22 value of the matrix is R2 plus j omega L2. So I am writing the expression as R2 is one resistance value and the inductance value I am representing as j omega L1 minus m. So why I am taking the intermediate value is j omega m. So for that reason I have taken L2 minus m. Okay. So now, so for this loop equations, what is the mesh analysis says? So for the first loop, the current is I1. So I am writing the drop across the resistor R1 I1 plus I am writing the inductive drop minus plus j times of omega L1 minus m into I1 plus intermediate value. So that is j omega m the current flowing through, that is I1 minus I2, is equal to V1. So finally what you can get, R1 plus j omega L1 into I1 minus j omega m into I2 is equal to V1. So this is your first equation. Then coming to the second loop, so j omega m into I2 minus I1 plus R2 resistive drop, R2 into I2 inductive drop, j omega L2 minus m into I2 is equal to 0. So if you substitute, if you simplify, so you can get minus j omega m into I1 plus R2 plus j omega L2 into I2 is equal to 0. So the two equations 1 and 2, if you substitute in the matrix form, you can get the same. You can get the same. So that means the magnetically coupled circuit is transformed to conductively coupled circuit by using mesh equations. By using mesh equations. Are you understand all of these, students? So this is your conductively coupled circuit and this is your magnetically coupled circuit. So no connections in this side, but in this side the connections must be there. So next, coming to the numerical examples. So first I am going for the introductory problems, then we are going for the mathematical problems. Okay, so here we have to go for the set of equations for the given circuit under mutually coupled condition. So two loops are there, so two currents must be there. So I am taking the two currents must be in clockwise direction. One is I1, another one is I2. So here the I1 is flowing with the starting dot of your JA inductance. I2 current is flowing with the ending dot of JB. So that means that mutual inductance must be negative. That mutual inductance must be negative. So I am writing the first equation. So here for the first loop, so R1 is there, JA is there, R2 is there. So it is with respect to I1 current. So R1 plus R2 plus JA into I1. That is the drop across the three elements. Then R2 is combination of I1 current and I2 current. So I1 current already calculated. So I2 current is minus R2 I2. Then the mutual inductance here I already told. So I1 current is a starting dot, I2 current is a ending dot, that must be negative. So with respect to which current? I2 current, minus M I2 is equal to Vs, is equal to Vs. Then coming to the second KVL equation. Second KVL equation. Okay. So your second KVL equation, first R2 is combination of two currents, I2 current and I1 current. So for I2 current, the drop is minus R2 I1 plus the second loop passive elements, R2 is there, JB is there, R3 is there. So R2 plus R3 plus JB into I2. Now we are writing the mutual inductance value with respect to I1 current. So minus M into I1 is equal to 0. So like this, you have to write the equations with respect to mutual inductance. So coming to the second example, so we are writing the KVL equations for the two currents I1 and I2. So the first loop, you don't have any inductance. The second loop, we are having two series inductance. Two series inductance. So these two series inductance, the direction of current, one is a starting dot. So here it is a starting dot, but here it is a ending dot. So that means this mutual inductance is negative. this mutual inductance is negative. Okay, so now I am writing the first loop equation. So how many passive elements are there? R1, R2 minus JC capacitance. Okay, so R1 plus R2 minus JC into I1, and R2 is combination of I2 current also. So minus R2 I2 is equal to Vs, is equal to Vs. So this is your first equation. So while you are coming to the second equation, so R2 is combination of I2 current and I1 current. The drop of R2 is minus R2 into I1 plus the second loop. What are the passive elements? R2, JA, JB. So R2 plus JA plus JB into I2 minus, so here with respect to first coil, the mutual inductance with respect to second coil current, so that is I2 only, and with respect to second coil, the mutual inductance with respect to first coil, so that current is also I2. So series connection of two coils, I already told, it is minus, it is minus. Okay, so minus 2 times of m into I2 is equal to 0. So like this you have to write the KVL equations. So going for the example 3. So in this example 3, so here it is a two loop circuit. So I1 and I2 are the two currents. We are writing the equations for I1 and I2 with respect to KVL. So R1 JA is the first loop elements. So JA, JB, R2 is the second loop elements. So here the I1 current is the starting dot. I1 current is the starting dot. I2 current is the ending dot. So for JA, I1 current is starting dot, I2 current is ending dot. Are you understanding? So for that you have to write the expression for the KVLs. So first loop RA and JA. So you are writing R1 plus JA into I1. So JA with respect to I2 current. So you are writing the drop minus JA I2. So the mutual inductance from JA to JB is M. So with respect to I2 current, we are writing minus M I2 is equal to Vs, is equal to Vs. So now coming to the second equation, so J is combination of I2 and I1. So I am writing minus JA I1 minus JA I1. So the second loop passive elements JA, JB and R2. So R2 plus JA plus JB into I2. So this is your second drop. Then the M value of I2 current both are in the second loop. So that means you have to get the 2 times of M you have to get. So with respect to first coil, second coil current, with respect to second coil, first coil current. So minus M I2 minus M I2 minus I1 is equal to 0. So finally you can get minus 2M I2. So I already told series connection of coils are there. It is opposing, minus 2M must be there. So here also we are getting minus 2M I2. So we are writing the M I1. M I1. Okay. So coming to the fourth example. So it is just a correlation of your previous example only, but the coil is represented in the primary side. So first side. So here R1 plus JA plus JB into I1 minus JB into I2 plus, so M is the mutual inductance between the two coils. So I1 I1 flowing with respect to first coil is starting dot, second coil is also starting dot. So that's why the M value must be positive. The M value must be positive, and the two coils are connected in series. The two coils are connected in series, so we have to get 2 times of M. So 2 times of M I1 minus M into I2 is equal to Vs. So while we are coming to the second equation, minus JB I1 plus R2 plus JB minus JC into I2. So due to the first coil current, so minus M into I1 is equal to 0. So like this, we have to write the equations. So coming to the fifth example, so here 3 mutual inductances are there. So JA to JC is M1, JA to JB is M3, JB to JC is M2. So it is a 2 loop circuit, 2 currents are there. So for that 2 currents, we are going for the KVL equations. Okay, so for first loop, so R1 plus R2 plus JA plus JC into I1 minus, so R2 plus JC into I2 minus, so M3 into I2 minus M1 into I1 minus I2 minus M1 plus M2 I2. So this is your first equation. So anyway, this drop and this drop already familiar to you. So now I am concentrated on mutual values. So here the I1 current is for JA and JC is mutually opposing. Mutually opposing, because I1 current JA is starting dot, JC is ending dot. So that's why while you are writing with I1, you are writing with minus sign. You are writing with minus sign. So similarly, so the coil JA and JB, I1 is the starting dot, but I2 is the ending dot. So that's why this is also minus sign. This is also minus sign. While coming to the JC and JB, so JC is a starting dot, ending dot. So JB is also ending dot. So that mutual inductance is plus. So plus M2 into I2. Okay. So now coming to the second equation. So second equation with respect to I1 current is minus R2 plus JC into I1, and the second loop R2 plus JC plus JB minus JD into I2. So these are the voltage drops across the parameters in the loop. Now coming to the mutual, so here plus M1 into I1, plus M1 into I1. So why you are getting plus M1 into I1 means I2 current is starting dot, I1 current is also starting dot. So plus M1. So next, with respect to M2, so the I2 current for JC is starting dot, for JB is ending dot. So M2 is negative. M2 is negative. So here also you can get M2 with respect to I2 minus I1. And for M3, so here it is a ending dot, here it is a starting dot, so it is also negative. So like this we have to write the expression for the equations. Next, coming to the numerical problems. So for the circuit, you have to go for the calculation of the currents using mesh analysis. So here the mutual inductance value they are given is J2 ohms, between the two coils J6 and J8. J6 and J8. Okay, so the first loop we are writing 4 minus J6 plus 4 minus J3 plus J6. So finally you can get how much? 4 plus J3 into I1 minus J6 into I2. So I1 current is starting dot, I2 current is ending dot. Mutual inductance is negative. Minus J times of 2 into I2 is equal to 100. So that is your first equation. If you simplify, 4 plus J3 I1 minus J times of 8 I2 is equal to 100. So coming to the second one, minus J6 into I1 with respect to I1 current plus 5 plus J6 plus J8. So 5 plus J14 into I2 plus, so here the current flowing through I2 is ending dot for J6, ending dot for J8. So plus J2 times of I2 plus J2 times of I2 minus I1. So for I2 minus I1, it is opposite. For I2, it is same. So that's why 2 times of M you have to get. 2 times of M you have to get. Okay. So now finally you can get minus J8 into I1 plus 5 plus J18 into I2 is equal to 0. So if you substitute in the matrix form, 4 plus J3 minus J8 minus J8, 5 plus J18, unknown values are I1 and I2, and right hand side is 100 and 0. So connecting matrix delta, so determinant is 4 plus J3 minus J8 minus J8, 5 plus J18. So if you calculate, you can get 30 plus J87. Then delta 1. So delta 1 is replace the first column by right hand side. So 100 minus J8, 0, 5 plus J18. So if you substitute, finally you can get the determinant value 500 plus J1800. Then delta 2, replace the second column by RHS. So 4 plus J3, 100 minus J8, 0. So finally you can get J800. Then according to Cramer's rule, I1 is equal to delta 1 by delta. I2 is equal to delta 2 by delta. So I1 is equal to, the final value you are getting is 20.3 at an angle of 3.5 degrees. And for I2 value is 8.7 at an angle of 19 degrees. So the units of current is amperes. So are you understanding the students for how you are solving the problems? Okay. So remember these concepts and go for different textbooks for different problems. Try to solve the solution. You have to get the unique solution only. Okay. So next, coming to the one more problem. So here it is a two loop circuit. So two currents you have to find with respect to the voltage drop across the voltage drop across the inductor J6. So that is V0. That is V0. Okay. So for this one, I am going for the application of the KVL. So here first, the I1 current at J3 is starting dot. The I2 current at J6 is starting dot. And I1 current at J6 is ending dot. So that means the mutual inductance must be negative for I1. Negative for I1. Okay. So now the total impedance in the first loop, 5 plus J3 plus J6. So finally 5 plus J9 into I1 minus J6 into I2 minus J2 times of I1 minus I2, mutual induction between coil 1 and coil 2. So that is minus J2 into I1 minus I2 and minus J2 times of I1. So once again I am recalling. So here J3 and J6, if you take for the first loop, they are connected in series. Once they are connected in series and they are opposing, so it must be multiplied by 2 times. The m value must be 2 times of m you have to consider. Okay, so for that reason finally you are getting 5 plus j5 into I1 minus j times of 4 into I2 is equal to 10. So this is your first equation. So coming to the second equation, so minus j6 into I1 plus j2 into I2. So how we are getting j2? Plus j6 minus j4. So finally you can get j2 into I2 plus j2 into I1. j2 into I1. So here the final value, if you substitute it for 0, so you can get minus j times of 4 into I1 plus j2 times of I2 is equal to 0. So putting in matrix form, so 5 plus j5 minus j5 j4 minus j4 j2 I1 I2 10 0. So finally go for delta, delta 1, delta 2 determinants, then calculate I1 delta 1 by delta, I2 delta 2 by delta, you can get the current values. So now what is V0? You have to find the value of V0. So the V0 value is voltage drop across J6 ohms. It is the voltage drop across J6 ohms. So what is the current flowing through J6 with respect to the direction or polarities given by the circuit? So I1 minus I2. So minus 6 into I1 minus I2. I1 minus I2. So finally you are getting the value as, so minus j4 into I2. So V0 value is voltage drop across the 6 ohm resistor. So that is minus 6 into I1 minus I2 and minus j 2 times of I1. Minus j 2 times of I1 because they are mutually coupled. They are mutually coupled. So finally you can get this V0 value is equal to minus j times of 4 into I2. So now substitute the value of I2 2.94 plus j 1.76. So finally you can get the V2 value is 7.04 minus j 11.76 volts. So like this you have to go for the calculation. So coming to the one more problem. So we have to go for the calculation of currents I1 and I2. So there is two coils. So the given circuit is magnetically coupled circuit. The mutual inductance between the two coils is J3 ohms. Coil 1 inductance, self-inductance is J5 ohms. Coil 2 self-inductance is J6 ohms. So now I am applying the KVL for the first loop. So minus 12 plus minus j4 plus j5 into I1. So voltage drop across the capacitor and voltage drop across the inductor. So here I1 current is starting dot, I1 current is starting dot, but I2 current is ending dot. I2 current is ending dot. So this mutual inductance is minus J3 times of I2 is equal to 0. So finally you can get, so J1 into I1 minus J3 into I2 is equal to 12. So this is your first equation. Coming to the second equation, so minus minus J3 into I1 due to the opposing mutuality, minus J3 into I1 plus 12 into I2 plus J6 into I2 is equal to 0. So from this you can write the I1 value as I1 is equal to 12 plus J6 into I2 divided by J3. So finally you can get 2 minus J4 into I2. So substitute this value in the first equation for the I as 2 minus J4 into I2. So then J into 2 minus J4 into I2 minus J3 into I2 is equal to 12. So finally you can get 4 plus J into I2 is equal to 12, or I2 is equal to 12 divided by 4 minus J1. So finally you can get 2.91 at an angle of 14.04 amperes. So once you calculated the I2 value, substitute in the I1 is equal to 2 minus J4 I2. So if you substitute, finally you can get the I1 value is 13.01 at an angle of minus 49.39 degrees. So dear students, so like this you have to go for the calculation of the magnetically coupled circuits with for finding the voltages and currents. So or you can go for magnetically coupled circuit equivalent diagrams of the T networks, and you can go for the calculation. So both calculations you are recommended for mesh analysis or nodal. So here maximum you have to go for the mesh analysis for simplicity only. So thank you one and all.